This book, chapter 15, day 1, gets us back to something we learned a while ago, line of regression. Specifically, we'll be looking at inference, which is a confidence interval. Well, we probably won't get to much of that today. We'll look at some notes for it, but I don't think the assignment really touches on it much. What is the layman's term for line of regression? Anybody remember? Line of best fit, exactly. There's other things you'll see, least squares, line of regression. It's all the same thing. Line of best fit, line of regression, least squares, line. And the formula for this, or the linear equation, is y hat equals a plus bx. And we learned this back in chapter 3. It's been a while. There's sure been a lot of information learned since then. A is the y-intercept, and b is the slope. Now, we do have some conditions for doing inference with a line of regression. The conditions are pretty similar from one thing to the next. The first one is observations are independent. Observations are independent. The relationship is linear. And we have some r values and r squared values that apply to that. Does anybody remember what values of r have to occur for us to consider it potentially linear? It's been a long time. It is. R has to be greater than 0.7. And this is an absolute value because r can be negative. So r has to be greater than 0.7. And r squared has to be greater than or equal to 0.5. Right, Adele, 0.5. So here's the thing. If your r squared is greater than 0.7, then your r squared will be greater than or equal to 0.5. If r is 0.7, it's just slightly less than 0.5 here. It's just has to be a little bit bigger. And the last thing, the standard deviation of the response, y, about the true line is the same everywhere. True line. Standard deviation of the response y about the true line is the same everywhere. A little of this we're going to get into today, not a whole lot. Most of today is going to just be reviewing line of regression and the stuff that we knew from last fall. Right. So, standard error always refers to the standard deviation adjusted for the sample size. At least that's the pattern that I've always seen. Standard error about a least squares line, or about the least squares line, which is the line of regression, is S equals square root the sum of the residual squared divided by n minus 2. Which is the same as saying it's the square root of the sum of y minus y hat, quantity squared, over n minus 2. So the residuals are the actual value minus the predicted value squared. And we use S to estimate the unknown sigma in the regression model. Now, if I were just doing this, I would let the calculator do this. And I think we'll have a problem where we'll have a look and see how we can make the calculator do this for us. Confidence interval. For regression. Specifically, we do a confidence interval on the slope. Quick reminder, confidence interval gives us some percent between in the middle, and we're saying that the slope of the true line is basically what we're going to be looking at. We're 95% confident that the slope of the true line falls between these two values. And the calculation for that is b, the slope of the line of regression, plus or minus t star times the standard error of b, which is the standard error of the slope. It's the standard error of the slope. And the standard error of b is calculated like this. It's S, the standard error that we have up here, divided by the sum of x minus x bar squared, the square root of that. And last lastly, almost about as much as an afterthought as anything, degrees of freedom equals n minus 2. Now, something to point out here. We're talking about slope. Where do we find slope? This is the slope. Okay. And that same slope, that's the value right here that you get out of your line of regression. That's your slope. All right. Again, a lot of this we're not going to be using today. We'll use it in the next class quite a bit more, but we've got it in the notes, and that gives us a head start for the next day. All right. Everybody with me? Do I need to go back? We're all good? No? Okay. Hands off. I'll give you a bit of time there. In the meantime, maybe I'll hum the Jeopardy tune to myself. Right? Come on, you guys all know it. All right. We are going to look on page 894, problem number 1. It's the Extinct Beast 1. So if you want to turn to that. .894, it's number 1, 15.1. It starts at the bottom of the page. It's called an Extinct Beast 1, and it's an extension of a problem that we did way back last fall. All right. And they give us some data in this. It talks about the Archaeopteryx. It's an extinct beast having feathers like a bird but teeth and a long bony tail like a reptile. And here are the lengths in centimeters of the femur, a leg bone, and the humerus, a bone in the upper arm, for 5 fossil specimens that preserve both bones. So here's what we've got. Femur. This is going to be in centimeters, and it'll be our x, and then our humerus. Thanks, sir. That'll be our y. So the values that they give us are 38 and 41, and 56 and 63, and 59 and 70. 64 and 72, and lastly 74 and 84. So what we really want to do first thing, once you get that copied down, is to copy it into the calculator. And we will want to put that in L1 and L2. L1 for the femur, L2 for the humerus. So let's do some line of regression work here. what we want to do is we want to find the line of regression and see what it'll tell us. So line reg in the calculator, we want a plus bx. Anybody remember where to find that? Stats, yep. Calc. Not this one. 8. I'm sorry, I thought I heard 3. Yeah, no, well, I don't know. You get old, you can't hear anymore. Too much rock music, I'm not sure. All right, line reg a plus bx. So our x list will be L1, that's the femur. The y list, L2. Frequency, leave that blank. If there's ever anything there, you leave it, you don't change it. Store the regression equation. Yeah, let's do that. To do that, you got to go to vars, yvars, function, and then wherever you want to put it, y1 is great. And then we'll calculate. And here's where you should get that r squared and the r value, where if you don't have that stats diagnostic turned on, you won't get that. So I'm going to write this down before I get too crazy. So my equation is y hat equals. I know it doesn't say y hat here. They just apparently can't program that into the calculator. Negative 3.66 is the a value, the y-intercept, plus about 1.2x. So I've got a equals negative 3.66, b equals 1.2-ish, r squared, 0.988, and r, 0.994. Yeah, come on. All right. So help me remember here. What does r tell? Anybody remember? How is r different than r squared? Yeah?
R is like the strength of the correlation, and then R squared is how well the line convexity is.
Well said. But what do you mean by strength of the correlation? In Yeah, how spread apart they are. Are they spread way out? The other thing R will tell us is if it's got a positive slope or a negative slope. So this is trending up because R is positive, but it doesn't say how much. It's not a steepness. That comes from this number. But yeah, this says how spread apart the data is. It's not very. The closer to 1 it gets, the better, right? And R squared is how good a prediction this y hat is. So we're going to get a good prediction about 99% of the time. Let's see if that doesn't fix it for you. I think that will. Okay. All right. There are just a quick reminder, there are two ways to calculate this. Some books use the ax plus b kind of in the same format as algebra where it does slope and then the y-intercept, which makes sense to me, but for whatever reason, Stats uses this, and I suspect that the graders for the AP test would be more likely to look for this. Not that that's wrong, it's not, it's just you got to make sure you're specifying slope and y-intercept and stuff like that. And this does it. By writing that, that tells them what you got going on. Okay. So the question here is make a scatter plot. So let's make the scatter plot with the calculator. You guys remember how to do that? So we're going to go to our stat plot. Make sure one is on but none of the others are on. We want the scatter plot with L1 and L2 being our X and our Y. Mark, color, none of that matters to me, if it matters to you. And then we can hit graph. Now mine's graphed it before. You'll probably have to get zoom 9 to get yours to come in like this. So you can see that the 5 data points that we have are very close to the line, very nearly perfectly linear. It says, do you think the femur length will be a good predictor for the humerus? Is there evidence in here that leads us to believe that we can predict one from the other? Yeah, about 99% of the time we can predict very accurately. So I'm going to say the femur length will be a good predictor about 99% of the time. And I'm just going to reference r squared equals 0.988 of humerus length. So really nothing new in this problem at all, just stuff that we haven't done in quite a while. So the next one I want to do with you, we're going to kind of skip through a couple parts of it because we haven't learned everything that we want to know, but part of it is not so much skipping as learning it in a problem. So this is going to be 15.5. It's on page 900. And it's the second part of this problem, an extinct beast 2. On extinct beast 2, it says, explain in words what the slope beta of the true regression line says about the Archaeopteryx. Got this funky beta symbol that we haven't defined yet. This is the parameter for slope. It's the slope of the actual line of all Archaeopteryx, okay, which we could never really know. So this is the parameter for slope. And what it will do is it'll do exactly the same thing that this slope does, assuming that this is a good sample. Let's say what B does. It is, B says for every for every 1 centimeter of femur length, what does the 1.2 do for the humerus length? Well, that's that multiplier of slope. If I put in 1 centimeter of humerus length, I'm going to get 1.2 centimeters of humerus length. That's not what beta necessarily says. This is how we would predict beta. But that is what the how you would interpret a slope. B. What is the estimate of B from the data? And what is your estimate of the intercept A of the true regression line? Well, we would estimate that beta equals 1.2 centimeters at this point. That would be our estimate. A is negative 3.66. How would we interpret that y-intercept of A? What's the x value for any y-intercept? Let me back up to there. Come on, you guys have had math before this, right? When you have a y-intercept, any y-intercept, what is the x value for any y-intercept? 0, right. So when we have 0 for 0 centimeters of femur length, the humerus equals negative 3.66 centimeters. That's what the y-intercept says. Does that make sense? No. First of all, you can't have a negative measurement, so that's a problem. Why would our line of regression say something like this? Does anybody remember what issues we have with line of regression and y-intercepts? I know I'm asking you to think back to like last September. It's tough. If I were to graph this situation, here's my y and here's my x, and perhaps this does something like this. And my data is out over here. Hello. Thanks, sir.
You're welcome.
What is it? What do we call it when we get outside of the range of our data? Does anybody recall? No? It's extrapolation. When you start getting too far outside of the data, you're in danger of extrapolation. And what we learned back in the fall, that clearly we've forgotten, which I don't blame you, we've learned a lot, is that the y-intercept for these lines of regression oftentimes makes no sense whatsoever in terms of the problem. And that's okay, because the y-intercept is too far away from the data to be something that we could consider reliable anyway. So these lines of regression are really only linear. We can only consider them to be linear in a short range within our data itself. Beyond that, we can't say that that line goes on straight forever in all directions. That just doesn't apply. So we've got to be cautious about extrapolation. All right, let's see if we can calculate the residuals for the 5 data points. and check that their sum is 0. So C, residuals. You don't need to calculate the residuals. The calculator has already done it. All you have to know is where to look for them. So I'm going to go ahead and go into a list. I'll zoom in a little bit here on the calculator. I'm going to go up to L3 and I'm going to add the residuals into L3. So to do that, I'm going to press second and then stat. See the list there? We're going to go into our list. And once you've made your line of regression calculation, your residuals are stored here. It might be in a different number than mine, but it's almost always right at the bottom or near the bottom. So we want to see what those residuals are. There they are. Now the residuals are the amount of difference between the line and the points in the graph. And you've got some points on top and some points on bottom. So if you took the difference of both of those, you should always get 0 or near 0 if there's some rounding. So I'll write these down in here in just a minute, but let's just check and see if the sum is 0. So if I go down to the bottom and ask it to find the sum of this, I'm going to go second, stat, again, list. I want to go over to math and find the sum of L3. And we get 1 e to the negative 12, which is not 0, but it's so small that second stat. Go over to math, and then look for sum, and then just tell it L3. Okay, so this number is 11 zeros and then a 1, a decimal 11 zeros and a 1. So I'm pretty sure that that's 0. We just need to take for granted that that is. So I'm going to delete that one because I don't think I need that one anymore. The residuals are negative 0.823, negative 0.367, 3.0425, negative 0.942, and negative 0.911. And the sum is 0. Oh, sorry. I'm writing all that and you guys can't see much of it. There we go. And let's see if we can estimate the standard deviation. So to do that, I'm going to come back to this guy right here. So we're going to estimate the sum of sigma. Now, I've got the residuals. They're in the calculator. So I'm going to use that here in L4. I want to square them, and I want to add them. So let's square them first. So I'm going to say, oops, wait a minute, I don't want to square yet. Let's put in L4. I'm sorry, L3. We're squaring the L3 list, and we'll square that. That'll give us our squared values. Now, I need the sum, and then I divide by n minus 2. Well, what's n minus 2 going to be? 3, right. Actually, I wonder if I could just divide by 3. So if I take L4 and divide by 3, and now, so I've got Now the last thing I have to do is take the sum and the square root of the sum. Hang on, I'll be with you in a minute. Let me finish this up so I can get this video. It's L4 minus 3. So I'm going to take the square root of the sum of L5. Square root the sum of L5. 1.98. So the sum, the S, is about 1.98. Okay. So going back, I took the residuals out of the machine, I squared them, I subtracted 3 each one, and then I took the square root of the sum. No, I subtracted 3. Because the formula is n minus 2, so that's the 3. Yeah, I subtracted 3. So, yes. Wait a minute. You're right, it does. What did I do? I think I subtracted 3. No, I divided. I keep saying subtracting, but yeah. No, I divided. Sorry about that. You divide by n minus 2. It's because of the subtraction that yeah. So, residuals, residual squared, residual divided by n minus 2, which is 3. Sorry. And the sum of the square root of the sum. Okay, thank you for clarifying that. I was saying that wrong for sure. Okay, all right.